Welcome back. So in this video, I'm going to address geometric series. I will begin with a finite one, and then I'll move into an infinite geometric series. Recall, geometric series is a series which is a sum where the second term divided by the first term is the same thing as the third term divided by the second term. In other words, you have what we call a common ratio called R. So if you have a common ratio called R, then the series is geometric. And in this case, it's finite because I stopped here. I'm not making it infinite. And this is a summation notation for this expanded version of the series. And I want to know the sum. Now, just before we even get started, just understand and know, and it's common sense to think, that if you have a finite series, the series converge. Now, I don't know what it's converged to, but I know it converges. It's just finite. You just add the terms one after the other, one by one, and you will get some sort of a sum. For this particular geometric series, we actually know the sum. The sum is going to turn out to be this expression down here. So let me walk you through this process first. How do I add these terms? You notice A1 is common, so I pull A1 out, and I need to know what this sum is. Recall from basic algebra course that x squared minus 1 is x minus 1 times x plus 1. And you may remember that x cubed minus 1 is also x minus 1 times this expanded trinomial. You could divide this by this using synthetic or long division, and you will get this. Now, we know x minus 1 is a factor because 1 is a root. If you plug in 1 here, you get 1 squared minus 1, which is 0. If you plug in 1 here, you get 1 cubed minus 1 is 0. So we know x minus 1 is a factor. You just need to find the other factors. If you divide this by this, you should get this. And if you divide this by this, you should get this. And if you do it, if you continue, you will begin to see a pattern. And you could actually prove this by induction if you want. But x to the n plus 1 minus 1 is definitely x minus 1. That's one of the factors. And the other factor is this sum. And you notice that there is a pattern. There is 1 plus x. There is 1 plus x squared, which is this. If I have x to the fourth minus 1, you could write this as x minus 1 times x cubed plus x squared plus x plus 1. So there is a pattern. I chose to go to n plus 1 because I want to end with n here. So this is 3, this happens to be 2. I really want to end with n. I don't want to end with n minus 1. So I decided to figure out what are the factors of this expression. And we could do this using the principle of mathematical induction to prove this. So that means if I divide this by this, I should get this. Okay? So if 8 is 4 times 2, then 8 divided by 4 is 2. Makes sense? And of course, 8 divided by 2 is 4. So if you divide this by this, you're going to get this. Now, I have the right, of course, to divide this by this, or to divide the opposite of this by the opposite of this. So I could say 1 minus x to the n plus 1 over 1 minus x, the two negative signs will drop, will still be this. In other words, if you look at this expression here, it resembles this one, right? Just replace x by r. And therefore, this has to be r to the n plus 1 minus 1 over r minus 1, but I flipped both. And it's better written this way. So this sum, this piece here is this. And therefore, if I want to know what's the sum of this finite geometric series, I just have to multiply this by a1. So if I multiply this by a1, I get my sum. This is the sum, okay? Does it converge? Well, that's a silly question. It's a finite. It has to converge. And this is the sum. This is the actual sum. And I'll work out a couple of examples, okay? Notice that we have n, this letter here, n plus 1, tells you the number of terms. You could see it here. If I get to r to the n, you might think I have n terms, but notice that this is a1 times r to the 0. So I'm actually starting with 0 and ending with n. So that means there are n plus 1 terms. So the number of terms always goes here. Sometimes you write n, sometimes you write n plus 1 or n minus 5, whatever the number of terms you have, that's what goes here. So this is the sum of a finite geometric series, and it's not that interesting. It gets interesting if we make it infinite. And if we make it infinite, it actually gets easier. So how do I make an infinite, a geometric series infinite? How do I write this? Well, you could just add plus 3 dots, right? And I want to know what is the sum. Well, we know the sum is going to be this when n goes to infinity. Does that make sense? And this is how you write it. Limit as n goes to infinity of the finite sum we just got. Okay? Now, a1 is just a constant, and n is your n is your variable, not n is going to infinity. So we need to think about the value of r. So I drew a picture here for you. So this is the number line for r. R could be less than -1, could be between -1 and 1, could be more than 1, could be 1, could be -1. I'm going to exclude them for now, and I'll deal with those two values separately. So let's begin here. So if R is between -1 and 1, non-inclusive, strictly between -1 and 1, when you raise that number to the n plus 1 power, it goes to 0. So you end up with a1 times 1 over 1 minus r. So this is the sum of an infinite geometric series where r is between -1 and 1. You can get them so fast, okay? Now, if r is more than 1 or less than -1, this is going to blow up, right? This is going to go to infinity. And infinity over a number is infinity. So the series, the infinite geometric series, will converge to this number, to this sum, I call this S, to this sum, if r is strictly between -1 and 1. And if r is greater than 1 or less than -1, it will diverge. Okay? So now I am going to address those two special values, 1 and -1. Okay? Now if you plug in 1 here, you're going to end up dividing by 0. So you don't want to do that. What you want to do is to rewrite your series, the original series, make sure it's infinite, like plus dot dot dot, and force r to be 1. And if you force r to be 1, you're going to get a1 plus a1 plus a1 plus a1 infinitely many times. Clearly, if r is 1, this series diverge. Imagine you have 2 plus 2 plus 2 plus 2 plus 2 infinitely many times. Okay, so that's easy. Now let's get to -1. If you replace r by -1, the infinite series becomes a1 minus a1 plus a1 because I'm multiplying by -1. Makes sense? Now, you may want to pause the video and think about why should this series diverge? And I'll show you a couple of ways to do this. So imagine I put parentheses. I'm not gonna move the constants around. I'm not going to say a1 plus a1 plus a1 minus a1 minus a1. I'm going to go in order. If I put parentheses here, I'll just get a bunch of zeros, right? So you could say that this series converts to 0. Or you could say, if I put the parentheses here, then you get 0 plus 0 plus 0 plus 0 plus a1. So you could make this go to a1. And I could actually make this series go to any number you could think of. I could make it go to 0. I could make it go to a1. I could make it go to half a1. You know, we could do that in class. So this series diverge. Why? Because it doesn't converge to a unique number. And therefore, this is the summary. Okay? If r is between -1 and 1, strictly between -1 and 1, this is a shortcut of how to say it, then the geometric series converts to this number. If r is more than 1, if r is more than 1 or less than -1, you could actually say it this way, right? If r is greater or equal to 1, or, not and, sorry, not and, but or less than -1, it means you're here. If R is here or here, which can be written like this, then the geometric series diverge. Sometimes it diverges to infinity, as the case with 1, and sometimes it diverges to not a unique value, not a unique limit, and therefore we say it diverges, okay? Now let's look at some simple examples. Consider this series. Notice that it is infinite. Notice that it is geometric. In fact, the common ratio is a half, which happens to be between -1 and 1. So we know that this series must converge. Where does it converge to? It converges to A1, the first term, divided by 1 minus the common ratio. Well, the first term is 1, and 1 minus R. R is a half. 1 over a half is 2. Consider another series. This is definitely a series. It is a sum. Now don't let the negative bother you. And subtraction is an addition. So that's what we mean by sum. And we know that it is infinite. And we also know that it is geometric. In fact, the common ratio is -1/2. This number is between -1 and 1. Therefore, this infinite series must converge to this value. And that value is the first term over 1 minus the common ratio. 1 plus a half is 3/2. You flip 3/2, you get 2/3. Let's do one more example using two different methods. Consider this number, 0.3 bar, which is 0.3333 infinitely many times. Okay, not a million times, but infinitely many times. Why is it that 0.3 bar is exactly 1/3? This is not an approximation. Show it to you in two ways. First method, take this 0.3 bar and write it in this expanded version. This is a compressed version. 0.3 bar is 0.3 plus 0.03 plus 0.003 plus 0.0003 and so on and so forth. And this is an infinite geometric series. And we know that the common ratio is 1/10, right? If you multiply this by 0.1 or 1/10, you get to here, right? That means, so we know that this number is between -1 and 1. Therefore, the series must converge. Where does it converge to? A1 over 1 minus R. A1 is 0.3. 1 minus the common ratio. 0.3 divided by 0.9 is exactly 1/3. Now let me show it to you in a different way. Now I already know that this is an infinite geometric series where R is between -1 and 1. So we know that there is a sum. Let's call that sum X. You can't always let something be whatever you want. Okay, I already know that this converges. That's why I called it X, or call it S if you want, sum. Okay, so what I'm going to do is I'm going to subtract this 0.3 or add -0.3 to both sides. I get this. Then what I'm going to do is I'm going to multiply the left-hand side and the right-hand side by 10. So if I multiply this by 10, I get this. And if I multiply this by 10, I get exactly the old X. Notice that this is true because it is infinite. In other words, if it is finite, let's say I have 10 terms only, it stops at 10 terms. 0.3 plus 0.03 all the way to the 10th term. And you subtract this 0.3. Now you have 9 terms left. And you multiply those 9 terms by 10, you're not going to get the old X because the old X has 10 terms. The fact that this is infinite, once you subtract one term and you multiply both sides by 10, you will get the exact old X. And now this becomes a simple algebraic equation. 10x minus 3 equals x. That means 10x minus x equals 3. And 9x equals 3. And therefore, x must be 1/3 again. Okay, so there are two ways to show why is it that 0.3 bar equals 1/3. And I'm wondering if you have ever thought of this number as an infinite geometric series. All right, take care.